Hi guys, what's up? The study that we're going to be doing now, this video, for now, is going to be focused on the aspects of meteorology that we can take advantage of for our flights, that we can fly farther, higher, and for more time. To speak of meteorology in the way that it's normally dealt with, in an abstract manner, distant, doesn't really help pilots to understand the life of the air, the movement of the air. Since our gliders don't have engines, we need to be able to use a subtle engine. In this case, the engine that we use is the movement of the atmosphere. We must take advantage of the movement of the atmosphere to use this in our favor. And there's no other way for us to understand these movements that the air does other than using the science of meteorology. In the same way that, for instance, the engineering tries to understand the forces that underpin the construction of a building, the laws that underpin these forces, that rule these forces, meteorology tries to understand the laws, the forces that run the movements of the air. So, meteorology is the only science, reliable science, that we can use as a base for interpretation of this engine, let's call it that, of the movement of the atmosphere that we're going to be using in our favor. The first important aspect that we need to highlight for us to go into the study that we're interested in is the issue of differences. If we pay attention in our day-to-day, in our lives in general, we will notice that the differences are fundamental for our existence. For example, you who are there watching my image, this is only possible thanks to the difference that there is between my image and the backdrop behind me. There must be a contrast, a difference in color, in hues, in shades, in light, differences. When we are speaking about the differences that matter for meteorology, more specifically for our flights, there are differences that are specific that we have to pay attention to. If we are very much aware of these differences, which will make a difference for us, we will end up by using them in our favor. We will end up using the differences, the perception of these differences, to fly in a more aware manner, more integrated, let's say, with the atmosphere. The difference that matters for our study, the difference to be highlighted, let's say, that matters for meteorology is the issue of density, that is related to temperature, which is related to the movement of our atmosphere. This camera that's in here in front of me is working thanks to a difference. In this case here, the difference is electrical. It is connected to an outlet where there is a positive pole and a negative pole. There is a difference in potential, electrical potential in this case, that generates the movement of the motor of the camera. In the case of the air, it is the difference that we have already spoken about in temperature and density. It's going to be the trigger of the movement of the air that we're going to take advantage of to fly. Let's clearly understand what is the polarity, what are the poles, what are the differences then that will be important for us to pay attention to when we're flying. For meteorology, the polarities are called high pressure and low pressure. This difference between high pressure and low pressure will generate movement, will generate wind, will generate thermals, the so dear thermals that we have, and we will have the descending drafts as well. All this movement is associated to this polarity, high pressure and low pressure. High pressures are portions of air, are parts of air, are pieces of air that are colder than the low pressures. Now, how can air be colder than other air? Why is one air hotter than the other? The first thing that we need to understand, guys, is air in itself is not heated directly by the sun. First off, the sun will warm up the surface of the Earth, and the surface of the Earth will then heat up the air that is in contact with it. So, for example, more heated surfaces will generate on these surfaces a low pressure, since this air on top of that surface will be warmer. On the other hand, a part of air that is on top of a colder, cooler surface or less heated surface, let's say, will transform into high pressure in meteorological point of view. The issue then is to educate our eyes to identify these high and low pressures, which is what we're going to be doing as of now. The first form for us to identify the high and low pressures is to perceive, for instance, that the Earth round receives light from the sun in different ways. We can already notice that the poles receive a lot less light than the line of the equator. The poles, in this way, are much colder than the line of the equator. So, the air that is in contact with the poles will be a lot colder than the air that is in contact with the line of the equator. So, we will have in this situation a high pressures, let's say, in the lines of the poles, and in the equatorial region, we will have low pressures. Another form of perceiving high and low pressures is when we have soil surfaces that are differently heated. For instance, between water on a lake and a plowed field, something which is typical for us mid-flight, is easy to perceive that the air that's going to be on top of the lake will be colder than the air that's going to be all over the plowed field. Once again, we will have high pressures and low pressures. Another form for us to identify high and low pressures is related to the amount of light that a surface received. For instance, if I have a surface where sunlight doesn't hit upon directly, that is, it's covered by clouds on a gray day, overcast day, this region, this surface, will be less heated by sunlight. That is, in this situation, we will have there a region that is likely to form a high pressure. On the other hand, a region that is being intensely lit by the sun, that's receiving sunlight since very early in the morning, this is a region that is likely to form a low pressure. That is, this is an interesting region from our point of view, for us to pay attention to, that we're going to take advantage exactly of this situation of low pressure that's happening on that region. What really interests us the most, as pilots, is to discover very quickly where our dear thermals are. That's what we're interested in. We want to take off and very quickly gain height as soon as possible, and as safely as possible. And the easiest way for us to visualize, to detect, let's say, where the thermals will happen, is to identify exactly the issues of high and low pressures. It is exactly by identifying which parts of the ground will probably be warmer than the rest. In order to identify this, we will highlight a few characteristics, let's say, a few peculiarities that will determine whether the soil will be warmer or less than another. The first aspect that we must pay attention to in order to determine whether that region is going to be a good producer of thermals is the issue of time of exposure to sunlight of the surface. For example, if a surface was exposed to sunlight since 6 o'clock in the morning, since sunrise, it's going to have a good potential for generation of thermals. On the other hand, another surface, which was, for example, in the shade because of a cloud layer, or because it was on a mountain face where the sun did not hit, it was on a shaded area of the mountain, this sort of surface will take longer to generate thermals. So it is important that these surfaces, in first place, be as long as they possibly can exposed to sunlight. Another fundamental aspect for us to pay attention to is the issue of the incidence of sunlight. Like we've just seen that the equator receives more sunlight and therefore heats the air more than the poles. For example, a face of the mountain turned east when the sun has just risen is a face of the mountain that will probably be a lot warmer than the opposite side turned west, since the sun is rising. In this way, paying attention to the incidence of sunlight on a surface, that's another aspect that we have to pay attention to. We will be able to determine whether that surface is going to be a good generator of low pressures. That is, whether it's going to be a region that will be abundant for us to find our thermals. But we may also find that there is a flat relief. There are no mountains, there are no inclinations, nothing faced preferably to the sun, so the region is flat. So in this situation, we begin to pay attention to other issues. For example, in this case of a flat surface, we will pay attention to the composition of the surface. A surface that is very damp, very moist with a lot of vegetation, in comparison with a surface that is drier, full of rocks and shallow, and even a plowed field that we've already mentioned, there will be a difference in terms of heating. The air over these surfaces, the air over a greener surface, a moister surface, will heat up less than the air over a drier surface, a rocky surface. Even if both of them have received the same amount of sunlight. And this is another aspect that we cannot leave aside. It is the issue of moistness of the surface of the soil. For example, even if I have a plowed field, which we've already seen that is a good generator of thermals, if this plowed field is moist, if it's just been irrigated, let's say, it is not going to be a good generator of thermals because the water, it steals heat. Water absorbs a lot of the heat from sunlight, even to be able to do its own evaporation. Our skin, when we sweat, does the same process. When we sweat, there is evaporation of water that is in contact with our skin, and this evaporation will reduce the heat of our bodies. In the case of a moist plowed field, it's going to be the same thing. It's going to cool that situation. The evaporation of the water on the surface is going to cause a drop in temperature. So the moistness is very important when we're flying and analyzing, when we're flying over the surface, analyzing it. We sometimes are in doubt, is there warmer than here? So we have to pay attention and we have to try to figure out which of the surfaces will be drier. Fatally, the drier of the surfaces is going to be the better generator of thermals than a moister one. Another thing that may happen is for us to have a very homogeneous surface, very similar. No inclination of mountains, no relief, everything is flat, and the surface to our eyes is very similar in terms of moistness. We can't really differentiate between surfaces in terms of moisture. That's where we have to use another aspect, which is the issue of color. The darker the surface, the more light it's going to absorb. A surface that is lighter will reflect more light, and in this way will heat up less. So the color would be a last aspect, let's say, not so important. The other aspects that we've mentioned up to here were more important. But color, let's say, serves to break the tie when we are in doubt between which of two surfaces is the best. If the surface is very homogeneous, it is the color that will determine which we will choose to go right or left or go straight ahead. Okay? Another aspect that we're going to highlight now is related to altitude in which the surface is found. For example, a surface that is at 1,000 meters of altitude, receiving a certain amount of sunlight, will heat up in an X way, let's say. The same surface, the same composition of surface, 1,000 meters below that, is going to heat up in the same way as a surface 1,000 meters above. But we will have something interesting happening there between these two surfaces that are in different altitudes. Surfaces that are higher will be surfaces that will generate low pressures, as compared to the more deeper surfaces like, for example, valleys, which will be generators of high pressures. Let's understand a bit how this happens. Why in higher regions I'm going to have lower pressures and lower or deeper regions I'm going to have higher pressures. Starting from the principle that we're talking about surfaces with the same composition, the same color, that are receiving the same incidence of sunlight, okay? So for us to understand this issue of difference of altitude, we will speak of the issue of thermal lapse. Close to the surface that is receiving light, sunlight in this case, the temperature is higher. It's higher than when it's farther away. Why does this happen? Because it is exactly the surface that heats up the air. When we go up to high altitudes, the temperature can be negative, below zero. So what happens then is that the temperature will decrease as we move away from the surface. What happens? Close to the surface, let's imagine that the temperature is at 30 degrees Celsius, at 0 meters of altitude. With the same surface at 1,000 meters of altitude, we will also tend to be at 30 degrees Celsius, except that at the 1,000 meters of altitude. Look at how interesting. I have a surface here at 0 meters of altitude at 30 degrees Celsius, and another surface here at 1,000 meters of altitude at 30 degrees Celsius. So if we were to draw a parallel between this altitude and distancing, we are moving away from the mountain, we will notice that distant from the mountain, we will have temperatures that are much lower to 30 degrees. I have 30 degrees down here, 30 degrees up here, but at the 1,000 meter level away from the mountain, I'm going to have low temperatures, very much less than 30 degrees. So what happens with this difference of temperature? We've spoken of the differences in the beginning exactly to be able to understand this. This difference in temperature is going to generate a movement, an instability of the air. I'm going to have, on top of mountains, a desire of the air to want to rise, to want to exchange place with this air that is in the surrounding area, because the air in the surrounding areas is very cold. It is a high pressure, whilst the air that is very up there, at the peak of the mountain, is low pressure. The exchange is very intense. On top of mountains, I'm going to have regions of low pressure exactly because the thermal lapse is going to be a lot more intense on top of mountains than it is in lowlands. Among the factors that we've just seen, the most important, the one that prevails over the others, is the issue of time of exposure of the surface. It is very obvious this, right, people? I mean, why do we make the best flights at noon, for example, or afternoon? Because we've had all morning of exposure of the surface to sunlight. The more time the surface is exposed to sunlight, the more heated it will be, and the more active and more abundant will thermals be. So this is the most important factor. This issue is very important because at times we are flying and we forget to pay attention to how long surfaces have been exposed to the sun. Sometimes we fly over a surface that has been sunlit at that point in time instantly when we're coming close to it, but this surface has been in the shade, and it might have been in the shade for hours and hours, and we did not notice this. So, no matter how much that surface at the moment that we are flying is sunlit, the chance of having thermals there is nearly zero, because it's been for a long time without exposure to sunlight. If we had a hierarchy in importance for these factors, it would be the following: time of sunlight exposure, angle of incidence of sunlight, altitude of the surface, moisture of the surface, and color of the surface, using cumulus as references. So far, we only paid attention to surfaces, which are the generator of thermals. The thermals are born on the surfaces, so this is the first important aspect that we cannot forego. Now, let's have a look at a different aspect, which is the cumulus. For teaching purpose, cumulus are nothing more than thermals in a visible form. Thermals, when they leave the ground, are carrying with them water vapor. Water vapor is invisible and will become visible exactly when it suffers condensation, when a cumulus is formed. So, while the thermal does not suffer condensation, or better said, as long as the water vapor inside the thermal does not undergo condensation, it is invisible. On the other hand, when the cumulus is formed, which are there, we have the cumulus over there, the visible part of the thermals is exactly the pom-pom that we can see here. Under this cloud, we have the thermal, here in an invisible form. In this way, it has shown itself, let's say. It has become visible. So the cumulus is a fundamental reference to be used when we are flying. The first fundamental aspect to be highlighted in a study of cumulus is the issue of seeing it from time to time. A photograph of a cumulus doesn't really help us very much to know whether under it the thermal is good. If we explore the visual aspect of a cumulus periodically, make a film of it, we will be able to identify better whether the thermal under the cumulus is at the beginning of its life cycle, in the middle, or even at the end. Like all meteorological forecasts, this is fundamental. For example, a satellite photograph shown on TV, that we see on TV, they try to show an animation of what's happening. So if there is a front coming from the south, they make it a point of showing the movement of the cold front, and not just a simple snapshot. In meteorology, it is fundamental, this issue of perceiving what is happening. What is the trend of the development of that phenomenon? A cumulus is no different. This is the first and most important aspect, the one that is the most important to be highlighted when we are looking at cumulus. When we are making a film of the cumulus, we will analyze several aspects of it. We will speak a bit about the aspect of the base of a cumulus. The base of a cumulus, guys, is a point from which the thermal, which was invisible, becomes visible. This is a point based on which condensation starts. So, a base with an X or Y face will tell us whether the thermal under it is active or not. A flat base, for example, like we can see here, it shows us that the process of condensation is happening. The cloud is active. The thermal under it is working. Based from the moment when the cumulus, the base of the cumulus loses its definition and starts to be malformed, threaded, as we can see here, this indicates that the thermal under it has lost its activity. It may even exist, but it is no longer as active as it was. So, bearing in mind that here we're looking at a snapshot. So, this is poor in terms of helping us to analyze these clouds. We have highlighted in the beginning the importance of analyzing this as a film, the cumulus as a film. Here we are looking at a snapshot only to take a look at the aspect of the base of the cumulus. In addition to the base of the cumulus, the contours of the cloud are also important in telling us whether this process of condensation is active, that is, whether the thermal under it is still active. And not only this, they will also tell us what part of the cloud, more to the right or more to the left or in the middle of the cloud, which is the portion of the cloud that is most active, which is the part where the process of condensation, of formation of the cloud, is better. This is exactly where we're going to be going to when we want to reach the thermal under the cumulus. In this snapshot, it is easy for us to perceive how there are cumulus with upper contours that are well defined than others. That is, in this cumulus here, where we notice the upper contours as being more defined, the thermal under it will tend to be more active than, for example, in this other cumulus here, where the upper contours are very badly defined, in addition to the base being very bad also. So here, coincidentally, where the upper contours are well defined, the base also follows this. That is, one confirms the other, that the thermal underneath it is actually active. Another important aspect for us to assess in a cumulus is the issue of vertical development. The more vertically developed the cloud is, always bearing in mind to see this as a film, the higher this vertical development, the higher will tend to be the activity of the thermal under this cumulus. So let's look again at this picture here. Once again, coincidentally, the cloud that is presenting the highest altitude, the higher vertical development, is showing us that the thermal, once again, is more active. You can see how much things match. The base is good, the upper contours are well defined, and the vertical development is also more accentuated than in the rest. So these are all aspects that are important for us to analyze in a cumulus. We also have the issue of the density of the cloud. Often the cumulus has parts that are denser than others. The parts that are denser of the cloud will be exactly the parts where the process of condensation is taking place more intensively. So how do we determine, how do we identify which part of the cloud is densest? We have already spoken about upper contours, about vertical development, and other as fundamental aspect that we highlight in terms of density of the cloud is the darkness of the base. A darker base, if I can only perceive, if I can only see the bottom, the base of the cloud, I can perceive that in the darkest part of the base, there is a trend to be there the densest part of the cloud. That is, the part that is most intense of the thermal. This is a fundamental reference to observe the base and to try to identify the darkest part of the base, which normally is associated to the densest part of the cloud. So the darker base of a cumulus is going to be related to a density, which we've just spoken about, and also related to the vertical development of the cloud. The higher the cloud, the more shade it projects, less light the base receives. A very dark base indicates that there is a good portion of cloud above it, which is exactly what we're looking at in this picture. The darkest part being shadowed by this large part of the cloud up here. So we have to pay attention when we are looking, when we pay attention to the darkness of the base of the cloud. For example, it's the cloud that creates shade for the base, and in this way generates a shadow, a darker part. Now let's look at something. If the sun is not straight up, if it is inclined, the shadow projected by the cloud is not going to be exactly on the same angle where the base is darker. That is, if the sun were straight up and the most protuberant part of the cloud were exactly this one, the darkest part of the base would be exactly under the more developed portion. If the sun is off to one side, the shadow would be projected here. The base under the most protuberant part would no longer be necessarily the darkest. So it is very important for us to pay attention when we're analyzing the hue of gray of the base, to pay attention to what is the angle of the sun, because it's going to project the shadow and it's going to fool us. Often, the most intense part of the thermal is not going to be exactly under the darkest part of a cumulus, because sometimes the sun is off to the side, and then we can be fooled and end up entering the thermal not at its strongest part necessarily. And to finalize our cumulus topic, let us speak a little bit about its life, the life cycle, the duration of their life. There are cumulus that we notice that last half an hour, 2 hours even. Other cumulus appear, and as quickly as they appear, they disappear. Why do you think this happens? There are several aspects, and they are complex, these aspects. Let us put here the easiest aspect for us to perceive, the aspect that's easier to understand. This aspect that we're going to deal with is related to the position of the sun. For example, a cumulus that is formed here, in a situation where there is no wind, let us pretend there is no wind on this day and a cumulus is formed and the sun is straight up, at 90 degrees straight up from the soil. This cumulus is formed, and with its formation, it happened that it created a shade for the region, the surface, that was generating its thermal. In this situation, this is going to be a cumulus of short duration. The duration of life cycle of this cloud is going to be short. In another situation, where we have a cumulus and the sun is straight up, but a windy day, we know that on windy days, thermals derive. That is, the cumulus is not going to be formed exactly over the region that generated it, let's say. There's going to be this derivation. The cumulus is going to be formed off to the side of the trigger, of the generator of the thermal. That is, this is a cumulus that tends to last longer, that tends to have a longer life cycle because it's going to project a shade on the neighboring area of the generator, and in this way will even potentialize the force of that thermal that generated the cumulus. This is an example of a cumulus that's going to last longer. So let's speak of another example also related to the life cycle of cumulus. I can have a cumulus on a windless day, hypothesis again, a windless day, and a cumulus, the generator down here, but now the sun is no longer straight up, it is off to the side, projecting the shade of this cumulus to the side. Once again, I have the trigger, the generator of the thermal, exposed to sunlight. And this is a situation where this cumulus tends to be long-lasting. Looking at the picture here, we can notice that, look, the thermals are projecting their shades. In this situation, we do not know what is the angle of the sun, but we can see that the shade is projected off to the side. So, this cumulus, the way that they tend to last longer or less as a function of the position that the shade is being projected in. If the shade is projected directly onto the place that generated the thermal that created the cumulus, it's going to be short-lived. On the other hand, if its formation does not create a shade for the generator, then we will have a very high likelihood of this cumulus lasting an hour and a half, maybe even 2 hours. But often we will have situations where there are thermals, but there is no cumulus. Often the humidity of the air is so low that the thermal is happening, it is bringing up a bit of moisture upwards, but the condensation does not occur. That is, we have thermals, but we don't have cumulus. These are the famous dry thermals. We call them dry thermals. In this situation, it's a bit more difficult to fly because the thermal becomes literally invisible. When we have the cumulus, as we've already said, the visible part of the thermal is coincidentally the cumulus, and so it's a lot easier to fly on a sky with cumulus than without. So we're going to speak now about other visual references as well. For example, in addition to cumulus, there are situations, there are movements visible to our eyes that will indicate probably where we have thermals or else downdrafts. Let us see how we can use these other visual references to identify where there probably are thermals and downdrafts. For example, if I observe carefully the vegetation on top of which we're flying, and I notice that there is, for example, some trees moving as if the wind were coming from here, and other trees moving as if the wind were coming from over there. These opposing wind directions are indicating the region of low pressure, exactly where the thermal is. These references are extremely important. They are very valuable when we are flying. We're flying low and we need to very quickly find a thermal. If we were paying attention to this movement, the differentiated movement of the wind close to the ground, on trees, vegetation waving, all I need to do is see a different agitation for me to pay attention, because this is going to indicate to me the possible region of low pressure, that is, where I'm going to find a thermal. Another excellent reference for us to identify the regions of low pressure where we have the thermals is exactly using the smoke to be able to identify the movement converging towards a direction. It is common for us to see smoke moving in opposite directions. They are indicating exactly a low pressure region. Another times, again speaking about smoke, I can perceive that, for example, there was smoke with a certain inclination, and it maintained this inclination for some time, and then all of a sudden it stopped to be inclined and started to go straight up. And this does not mean, guys, that the wind that was blowing here stopped blowing. Apparently, that is what we see. But what can be happening behind this phenomenon? The smoke was inclined and began to rise straighter. Why do you think that smoke that previously was inclined stopped being inclined? Let us look at this with meteorological eyes, using high and low pressures. The smoke that previously was like this and started to rise more vertically is trying to tell you that there may be low pressure here, or even in the smoke itself. This lack of inclination of the smoke can be even inverted, and it may begin to incline to the other direction. This does not mean that the wind has changed. It can be associated exactly to a thermal rising here, a low pressure rising here. It can also happen that smoke that had already some level of inclination increased this inclination and nearly leaning against the ground, and only after a certain moment it goes straight up vertically. This can show us that this situation is indicating probably a high pressure here, that is a downdraft, and a low pressure here. It's interesting, isn't it? Looking at the events around us with these eyes, high and low pressure, where is the wind coming from and where is it going to? Why did it change direction? Why did it accelerate? Why did it decelerate suddenly? Everything fits in like a puzzle. The issue of seeing the air in high and low pressures is not luxury. It is not because we want to put in the study in a more cult form, talking about low and high pressures. It's a practical issue. It's easy for us to perceive how useful it is to visualize it in this way, high and low pressures. And pilots that learn to interpret the movements of the air in this way, looking to highlight where we have high and low pressures, they will fly a lot more interactively with the air. In addition to finding much more easily the thermals, they will also be able to avoid downdrafts. The issue is not only finding where thermals are, the issue is, for example, when it comes time to leave the thermals, when we've already gained enough height and want to start flying for a distance, they will try to avoid the high pressure zones. We have broken down here the situations that will show us where we can find high pressures and low pressures. And we can always try to follow along the low pressures. We should avoid at every cost flying in high pressures. Not only when we want to gain, but also when we want to do a distance flight by dropping less, losing less height. Cumulus congestus. This name already wants to suggest that cumulus is a bit congested. It's become huge, it's gone beyond just a simple cumulus stemming from a thermal, and it has become big, and the fact that it become big can bring a few problems for us. In particular, problems related to safety. When a cumulus reaches a magnitude that we begin to call it a cumulus congestus, it begins to become difficult to come down. Often we are flying and go into a cloud and then have difficulties in coming out. That is, after a certain size, the cumulus stops being beneficial to our flight and begins to be a hazard. The hazard of cumulus congestus is exactly the fact that once we are inside the cloud, can no longer come down. It's a turbulence that is very strong. We have difficulty in controlling the parapent or the hang glider, and this in itself is already a problem in our flight. When the cumulus congestus is very congested, let's say, we can start to call it cumulus nimbus. A cumulus nimbus, guys, is a cloud that practically everybody's already heard about because it is the big ghost, it's the monster, let's say, that ruins our skies. And the cumulus nimbus really is very problematic for our practice of hang gliding. So now let's have a look then at the cumulus nimbus. This cloud is very interesting to be studied, fundamental for us in particular in relation to safety. It is a cloud, let's say, that is involved in a series of taboos. Many people feel that when a cumulus nimbus is raining, the danger is over and the cloud is dissipating and we can start flying. Unfortunately, that's not the case, guys. The cumulus nimbus not always becomes harmless from the moment that it begins to rain. Let's try to understand exactly how a cumulus nimbus works. The cloud presents basically three phases: the phase of formation, the phase of maturation, and the phase of dissipation. In the formation phase, the cumulus nimbus is still not really a cumulus nimbus. In reality, every cumulus nimbus begins as a normal cumulus that grows upwards and sideways, and the base becomes increasingly darker. It begins to reach a magnitude that we call a cumulus congestus, and then from cumulus congestus it continues to grow. Increasingly more, the base gets darker, the cloud becomes increasingly broader and higher, and this is the formation phase. There still is no rain, there's still no thunder, but there already is a large chance of that cumulus becoming a cumulus nimbus. When it grows a lot from a certain moment on, the mass of water, the quantity of water that there is inside the cloud is huge. It's very big. And all that has weight in suspension in the air. When this weight becomes excessive, when the cloud is too charged, what happens? The updrafts, the thermals, are a set of thermals that we have under a cumulus nimbus, right? This set of thermals can no longer support that quantity of water up there. What happens from this moment on? The cloud begins to rain. Actually, every cloud rains in this way. There comes a moment when the updrafts are no longer enough to maintain the water in suspension, and the cloud collapses in the form of rain. Not every one of them in the form of rain, but in the case of a cumulus nimbus, necessarily in the form of rain. What happens? When the cloud is being formed, the dangerous zone for us to be flying in is exactly under the cloud. Under a CB, which is in formation, we cannot come down. We're going to be rising from every point. We're going to fly 3 kilometers this way, 3 kilometers left, 3 kilometers right, and we will not be able to lose height. There's going to be a huge low pressure in that region where all that air is going to be rising. In the next moment, in the maturation phase of the CB, this air that was rising, that region that was a low pressure, will no longer be a low pressure region and will begin to transform to become a high pressure. It's still not a high pressure. It's stopping being a low pressure. In other words, if we're flying there, we will notice that all of a sudden we don't rise so much, or we stop rising, and that the cloud is very dark. Another thing that we will notice is that in the maturation phase, the cloud begins to thunder. That is, if we are under the cloud, we are in a region that is extremely dangerous because the cloud is going to collapse literally on top of us. And we will go down with all that water and all that heavy winds, and we're going to have to land. So when the cloud is in the maturation phase, the dangerous region for us to be flying in is in the neighboring region of the cloud. Why? The maturation phase is a phase that lasts very little time. The formation phase, of which we've already spoken, is gradual, it is slow, it can last 2-3 hours even. And after a certain moment, when the formation ends and maturation begins, maturation in itself lasts 15 to 20 minutes tops. In maturation, the cloud will be undergoing a transformation and will start to dissipate. This is going to happen in 15 minutes. So, when maturation begins to happen, I have approximately 15 minutes to move away from the cloud. Why is it important for us to move away from the cloud when the maturation phase begins? The maturation phase is announcing the dissipation that's going to be dangerous for us. In dissipation, the cloud, which was an entire low pressure and had all that mass, that's going to begin to collapse. When this cloud begins to collapse, in that region where it's raining, where the cloud is evaporating, where it's ending, there is the formation of a high pressure. A huge high pressure is formed right there, very violently. So if I'm in the neighborhood, flying, what's going to happen if in a region I have a high pressure? The neighboring region, the entire neighboring region, on the other hand, is going to be low pressure. So I'm going to have problems in losing height when I am flying in the region of a cumulus nimbus, a CB that is raining. I won't be able to lose height. Without counting those heavy winds close to the ground that is going to be blowing strongly coming from the direction of the cloud. So this is very much a problem. A cumulus nimbus, when it is in the phase of dissipation, when it's raining, it is extremely dangerous, nearly even more dangerous than in the formation phase, because the violence of this manifestation of the dissipation is much higher, much more intense. Everything happens very quickly, and the lack of control, let's say, is a lot higher. In dissipation, I have to be at least 15-20 kilometers away from the cloud in order not to suffer any interference, let's say, insofar as I might lose control. So now all we have to do is identify the formation phase, the maturation phase, and the dissipation phase. If we pay attention to strict technical detail, meteorology does not perceive these three phases exactly in the same way that this study does. That is, we are exposing these three phases in a slightly different manner for teaching and practical purposes. In the phase of formation, we will perceive that the base of the cloud is progressively darker, gets darker, and the contours, the upper contours of the cloud are well defined. And another thing, we notice that all the wind in the region tends to converge towards the cloud. Now we are speaking of the formation phase. The maturation phase, modifications begin to happen. For example, the upper contours of the cloud, in particular way at the top, they begin to lose definition. The ice begins to fall from up there. It is possible to see this. We can see that the top of the cloud, the anvil of the cloud, begins to lose definition. This is the maturation phase beginning to happen. There is no rain yet. The maturation phase, we still do not see any rain. But in the maturation phase, which is already dangerous, we begin to hear thunder, even if there's still no rain. Inside the cloud, electrical discharges begin to happen, and we can already hear the thunder. Another thing that we perceive in the maturation phase is that the wind that in the formation phase blew towards the cloud, in the maturation phase stops blowing, or else begins to blow increasingly slower. This perception of the direction in which the wind was blowing and the intensity is very important and will help me very much to identify this change in phase of the formation to maturation. And finally, when we are speaking of dissipation, it becomes easier to perceive the cumulus nimbus in dissipation because it's already raining. We can see the wind blowing from the clouds towards the neighboring regions, so all of this is much easier to be perceived. Now, to perceive that the cloud has already gone into the dissipation phase is a bit too late. I must foresee this event, and I must then check this when the cloud is no longer forming and beginning to mature. This is the important phase for us to perceive. I cannot lose this moment of transformation from formation into maturation, because once the dissipation has begun, I am already in hot waters if I'm too close to the cloud. Well, guys, in order to close, often we will be on the ramp ready for takeoff, and everything that was mentioned in this way here, apparently so simple, is not so easy for us to identify there. Sometimes it's a bit more difficult. Things happen in a more subtle manner. When this happens, then we haven't got that much choice. Either we send a friend ahead to test the flight, or else we wait one or two, a group of vultures to fly ahead of us, and we follow along with them and use them as our windsock. This is the easiest way for us to take off and to make sure that we make it to a thermal. It's a lot easier than all this work that we've done here. But I think that it's a lot more fun to fly in integration with this logic, this meteorological logic. It's a lot more fun. We don't even need to fly farther nor better than the others. All we have to do is to be integrated into nature, to play around with these movements of the air. That this is already in itself a lot of pleasure. We don't really need to gain 2,000 meters. We don't need to reach the base. We don't need to fly for 5 hours. The simple interaction with these forces of nature is already a miracle, is already fantastic. The flight in itself in this way is even freer than in any other way.